Welcome to our 7th video. This one we're starting with intermolecular forces, and we're going to start by really talking about dispersion forces. Forces that exist between molecules are called intermolecular forces. These are why when you spill water, you don't just see random atoms flowing everywhere, and your water kind of stays together, at least a little bit. These are really the compounds that keep our molecules together. It's not what keeps the atoms together. This is not what keeps hydrogen to oxygen. This is what keeps water to water. Chemists organize intermolecular forces, commonly IMFs, based on the structural features that give rise to the forces. Basically, what types of molecules will have these types of forces. We have 4 main types of IMFs. Our first one occurs whenever we have ionic compounds, and we basically just call these our ionic forces. These are the attractions between cations and anions. It's not really quite an intermolecular force. It really does keep the molecules together, sort of, but you don't really have molecules when you're dealing with ionic compounds. Molecules are atoms covalently bonded together. The reason we're calling this an intermolecular force is because it will hold molecules stronger than any of our others. This is kind of it's stronger than all the others, but not really technically one of the others. So just keep in mind that ionic compounds are held together the strongest. Now, our next intermolecular force, which is our main first intermolecular force, if you will, whenever there are hydrogen bonds. And they occur whenever we have a polar molecule that contains hydrogen and either nitrogen, oxygen, or fluorine. So, hydrogen and nitrogen, sure. Hydrogen, oxygen, like water, sure. Hydrogen, fluorine, sure. Just nitrogen and oxygen, no. You have to have a hydrogen and one of those 3. We'll talk about those later, but we call those hydrogen bonds. These are our second strongest. They're weaker than ionic forces, but they're still stronger than the other 2. Next, we have our third type of force. These occur whenever we have polar molecules, polar molecules, and they are called dipole-dipole forces. They are the forces that exist between the positive and negative ends of those polar molecules. Now, this actually does mean that anytime we have hydrogen bonds, we also have dipole-dipole forces. Hydrogen bonds are actually kind of a special type of them. What we typically, though, report is the strongest force that's in effect. So, if we have hydrogen bonds, we're not really going to talk about our dipole-dipole forces. Even though they're polar molecules, which means we have them, we care mainly about the hydrogen bonds. Our fourth type of force, though, occurs in nonpolar molecules, and we call them our London dispersion forces. Most of the time, we'll call them London dispersion forces, but sometimes we just call them dispersion forces. London refers to the guy who actually discovered them. Now, these are actually, we're going to talk about soon, prevalent in every molecule we have, but we really, as I mentioned before, only really report them when we're dealing with the nonpolar molecules because we don't really have anything else stronger to report. These are our weakest. But those are our 4 types of forces. London dispersion forces, we're going to start with, are our weakest force. But as I mentioned, they can be found in any molecule, and as I also mentioned, we sometimes just call them dispersion. So please don't get too confused by that. They occur whenever a temporary, kind of instantaneous dipole forms due to an uneven distribution of electrons around the nucleus. A dipole typically refers to a nonpolar molecule. We talked about these before, when we have a partial positive charge and a partial negative charge. Now, that is really where dipole-dipole forces come from. This is attracted to the positive ends of other molecules and this to the negative ends. However, in nonpolar molecules, this is our common distribution. The electrons can basically likely to be found on either side of this bond. It's not really more likely to find it or unequally shared. However, if we think of electrons and remember that they're moving, we're likely to find them really in anywhere around these orbitals, if you will. Occasionally, though, we may find an electron distribution similar to this. Now, please note, this is not really quite what's happening with electrons. They're moving in an orbital. We've talked about hybrid orbitals. We've talked about multiple bonds, etc. It's just an easy way to describe it. But at some point, if they're kind of moving around, they may temporarily all be mainly on one side, which means it's like we have a temporary partial negative charge and a temporary positive partial charge. Now, if one molecule can do it, other molecules can do this, which means temporarily we have a dipole-dipole force going on. Now, that's, gone very quickly because electrons are still moving, but we temporarily have this attraction, and that is strong enough to keep some molecules together. Not very strongly, but that's our London dispersion forces. Now, due to the weak nature of these, and really Coulomb's law, it's really only significant when molecules are close together. So these mainly apply when you've got a molecule next to a molecule and both of them are doing this. And like over a far distance, not really. Most of these forces actually really only occur on close distances. Now, close on the electron scale, not close on our scale. Now, the strength of our dispersion forces, though, increases with what we call the polarizability of a molecule, which basically represents the ease with which our charge distribution in a molecule can be distorted. Sometimes we call this the squashability, if you will, of our electron cloud. It basically means how likely are we to have our electrons in one area by themselves. And the tighter this is, the less likely they are. The bigger it is, the more likely electrons are going to kind of be spread out, I guess, enough that they'll randomly be in one big giant group on one side. Sorry, I had two typos. Polarizability typically increases with the number of electrons in an atom or molecule, or it'll increase when the molecular weight increases. Basically, the more electrons we have, the more likely that a lot of them are going to be in one area to sway this, if you will. And the heavier this is, the more likely this will actually have some significant pull on other molecules. Finally, though, dispersion forces will also increase with the presence of pi bonds, when you've actually got stronger bonds going on. You've got more electrons kind of concentrated, you've got this more kind of overlapping, this more surface area so that you can actually have electrons in contact, and thus a little bit higher dispersion forces. Main one I'd like you to focus on, though, is they increase with our number of electrons. Common example then would be, with the following molecules, which ones are likely to have the strongest dispersion forces, or the strongest intermolecular forces. Maybe they won't even tell you it's dispersion. Hopefully you quickly realize that since they're all bonded to the same thing, they're nonpolar, and as I mentioned earlier, that means dispersion. What we got to look at is the total number of electrons. And when you compare these, you'll find that the Cl2 molecule has much more electrons than these, which means that this would be our strongest intermolecular force. Even though they're all London dispersion, dispersion forces get stronger with more electrons. So, welcome to intermolecular forces. Thanks for watching.